We are discussing random vibration of discrete multi-degree freedom systems, that is multi-degree freedom system with finite degrees of freedom. So, in the last class we looked at the nature of equations of motion for multi-degree freedom systems, and we noticed that in many cases or in almost all cases the coordinates would be coupled, and the coupling between coordinates is manifest as one or more of the structural matrices being non-diagonal in nature. We showed that through a transformation we can remove this coupling, that means we can diagonalize the structural matrices using the matrix of eigenvectors associated with K and M matrices that helped us to define the notion of normal modes and natural frequencies, and these normal modes had an interesting property or most useful property, namely the orthogonality property that helped us to uncouple the equations of motion. And we had a problem in dealing with damping matrices because the modal matrix derived from undamped free vibration analysis would not uncouple the damping matrix unless damping matrix is of a certain kind. So, we assume that the damping matrices that we are going to consider are such that the undamped normal modes uncouple the equations of motion in presence of damping. Towards the end we also derived the input output relations in the frequency domain. So, we will continue from here. We will spend some more time on input output relations in time and frequency domains for deterministic excitations, and then analyze the response of the system for random excitations. Now, let us consider a multi-degree freedom system with s the degree of freedom driven by an unit harmonic force. That means, I consider the equation of motion to be in the form mx double dot plus cx dot plus kx equal to f into e raised to I omega t. This f is a vector whose entries are 0 except for the sth entry, which is 1. So, we call x rs of t as response of the rth coordinate due to unit harmonic driving at the sth coordinate. So, we are interested in steady state response. So, the question that we are trying to answer now is what would be the response at say rth degree of freedom for as t tends to infinity when we are driving the system at s degree using an harmonic excitation. So, we can start by assuming that the response of the system remains harmonic at the driving frequency. So, we can assume that as t tends to infinity x of t is some x naught into e raised to I omega t. This would make x dot as x naught I omega e raised to I omega t, and similarly acceleration is derived as shown here. So, if we now substitute this into this equation, the governing equation. So, I get this is the acceleration term, this is a damping term, this is a stiffness term, this is a driving term. So, if you rearrange we get this equation where we get a matrix now minus omega square m plus I omega c plus k into x naught into e raised to I omega t is equal to this. E raised to I omega t cannot be 0. So, from this we conclude that this matrix into x naught is equal to f. So, this resembles the equilibrium equation that we get in static problems like Kx equal to p, except that the stiffness matrix here is now function of damping matrix and the mass matrix, and also it has a frequency parameter appearing here and it is complex valued. So, this matrix we call it as dynamic stiffness matrix. It is analogous to the static stiffness matrix. The prefix dynamic connotes the fact that the matrix is function of driving frequency, damping matrix and mass matrix. So, we can get x naught by inverting this dynamic stiffness matrix, that is a direct approach, or we can try to see if we can diagonalize this matrix. So, to do that we assume x of t is x naught e raised to I omega t, and for x of t I use the transformation phi z of t where phi is the matrix of eigenvectors. So, x of t is phi of z naught e raised to I omega t. So, this phi matrix has this orthogonality property, namely phi transpose m phi is I and phi transpose k phi is a diagonal matrix with the diagonal entry being the square of the natural frequency. We also assume that C is classical, that would mean phi transpose C phi is also diagonal, and we denote the diagonal entry in the form 2 eta n omega n. So, we substitute this into this equation now, and we use the orthogonality property, we pre-multiply by phi transpose. So, we get this. Now, by taking phi inside here and phi transpose inside here, I get this as minus omega square phi transpose m phi plus I omega phi transpose C phi plus phi transpose k phi into z naught is now phi transpose f. Now, phi transpose m phi is diagonal, it is an identity matrix because that is how we have normalized the modal vectors, and phi transpose C phi I have written as capital gamma. It is a diagonal matrix with diagonal entry being 2 eta n omega n. Capital lambda is again diagonal with diagonal entry being omega n square. So, this matrix is now diagonal. So, we can easily invert it, this is a straightforward exercise. So, if we now write in longhand, so if I now consider the nth element in this vector z naught, it will be given by phi transpose n k f k divided by the diagonal entry in this dynamic stiffness matrix in the transformed coordinate system. So, I get this expression. Now, the numerator here can further be simplified because we have taken f to be such that all the entries except the sth entry is 1. So, therefore, this summation really contributes to only one term, and that is when k equal to s, f k is 1. So, I get here in the numerator simply phi s n. So, z0 n is given by this, the prefix 0, subscript 0 indicates that we are talking about amplitude of z of t, and n is the contribution from the nth mode. So, now we can write the expression for response in the original coordinate system. So, as t tends to infinity, I have the response as phi z naught e raised to I omega t. Therefore, if you take now the rth element, it is given by the summation n equal to 1 phi r n z0 n exponential I omega t. For z0 n, I have just now derived this expression. So, if I plug it here, I get this expression, and if you now look at the amplitude of the response here, I can write it as h r s of omega, and that h r s of omega is now displayed in terms of a modal summation. This is quite different from considering the inverse of this matrix and looking at the rth element. This is a brute force inversion, whereas here it is done using the normal modes. So, I have x r s of t is given by this term multiplied by e raised to I omega t. So, this is our frequency response function. So, h r s of omega means response at rth degree of freedom when s degree of freedom is driven harmonically at omega unit harmonic driving at sth coordinate. So, you can see here that x r s of t is same as x r of t. This is known as reciprocity relation. It is a kind of a symmetry that we expect in these problems. This frequency response function is also symmetric. If I now assemble all these h r s of omega for r equal to 1 to n and s equal to 1 to n in a square matrix, we can call this matrix as matrix of frequency response functions. It is symmetric, but it is not Hermitian, that is h r s of omega is h s r of omega, it is not the conjugate of that. So, now we have two representation for h of omega. One is the direct inversion of the dynamic stiffness matrix or in terms of the modal summations. The direct inversion of stiffness dynamic stiffness matrix appears conceptually simple. There is no coordinate transformation, you have to simply invert a matrix, but it is computationally difficult to implement. In computation, we seldom like to invert matrices. So, this is not a preferred way of computing frequency response function. The calculation of frequency response function as a summation or modal contribution is computationally easier to implement, and an important feature that we have to notice here is that this modal summation, although it is written as n equal to 1 to capital N, it is not necessary that we need to include all the modes in our calculation. In many applications, the first few modes contribute significantly to the response, and we can as well ignore the contribution from higher modes or apply a correction for that, for ignoring, and I will take up that issue later in the course. But right now what is important to note is that in this summation we need not include all the modes. In fact, it is not advisable to include all the modes, because when you make discrete models for continuum problems using say finite element method or any of the method of weighted residuals, the accuracy of higher modes are much less in comparison with accuracy of the lower modes. So, there is no reason why we should include all the modes. In a model with say n degrees of freedom, we can trust only 1/10 of the modes typically, it is a thumb rule. So, in that sense summing over all modes is a formal representation and it is seldom done in actual practice. Now, to see a simple example illustration of what we discussed, suppose we consider a 3 degree freedom system. Suppose if I drive the first degree of freedom harmonically as e raised to I omega t. Now, I have xrs of t is hrs of omega exponential I omega t. Suppose I consider now response, these are all steady state response. So, x1 of t, I call it as capital X11 of t, it is written as h11 of omega e raised to I omega t. This means that I am driving at the first node and measuring the response at the same node. x2 of t in this case will be x21 of t, because I am measuring response at 2 and driving at 1. Similarly, this is x31 of t. So, this is the matrix of the frequency response functions, and to construct these elements you need to do this exercise of driving each of the degree of freedom harmonically and finding out the response at all other DOFs and assembling the solutions that you get. For each one of such calculations you will be able to fill up one row and one column of the frequency response function. A simple numerical example, we consider a 3-story building frame. We use a shear frame model, that means we assume that slabs move parallel to each other resembling shear deformation, they move like slices of bread under harmonic displacement. So, we are interested in dynamics of this frame basically in horizontal direction in its own plane. So, given that we can make a simplified model for this structure as a 3 degree freedom system, where this M1, M2, M3 are respectively the masses of these 3 slabs. We assume the slabs are lot more heavier than the columns, and the contribution to stiffness is made essentially by columns, because we assume that slabs are infinitely rigid in their own planes. So, K1 would be, for example, 2 into 12 EI by L cube, K2 will be similarly 2 into 12 EI by L cube, and so on and so forth. So, I have suggested some numbers. EI is the flexural rigidity of each of the columns, it can be taken as this number, and another data that we have is that damping is 3% for all the modes. All modes means the 3 modes that are possible in this model. So, we can draw the free body diagram for M1, M2, M3 and represent all the forces. So, we can set up the equation of motion by summing the forces in horizontal direction, and we get 3 equations. These are the 3 equations, and we can arrange this in matrix form. This is the mass matrix, this is the stiffness matrix. We can see that mass matrix is diagonal, stiffness matrix is fully populated and it is non-diagonal, it is symmetric, mass is also symmetric. So, we can now consider the eigenvalue problem associated with this K and M matrices, and the characteristic equation in this case is given by this. Omega square is as the square of the natural frequencies, and if you expand this determinant you get a 6th order polynomial in omega, or a cubic polynomial in omega square, and if you solve this equation we get 3 roots displayed here, and associated with each of these eigenvalues I can compute the eigenvectors. This is the first eigenvector, this is the second eigenvector, and this is the third eigenvector. This matrix phi matrix is now normalized with respect to mass matrix, and based on the value of damping given as 3% for all the modes, we can construct the C matrix. So, we are given gamma as gamma nn is 2 eta n omega n, and I have phi transpose C phi as gamma. So, gamma is given. So, from this equation we can compute gamma. Brute force method would be C will be phi transpose inverse gamma phi inverse. Actually, we can avoid inverting the modal matrix by using orthogonality. I would not get into those details, it is possible. You can see the discussion in the book by Clough and Benzin, Structural Dynamics. In any case, we can get the C matrix. We need C matrix if we are going to compute FRF by direct inversion of the dynamic stiffness matrix. Otherwise, this matrix need not be computed. We can directly use the etas and compute the FRF purely by manipulating the expressions in the transform domain. So, this C matrix is provided for sake of completion. This C matrix again is symmetric and fully populated. If you carry out the numerics, this is plot of H11 of omega. These elements of frequency response functions are elements of FRF matrix are complex valued. So, I have displayed here the absolute value and the phase. So, x axis shows the frequency and this is the amplitude of the frequency response function, and we see that it peaks at the 3 natural frequencies which we have computed, and this is the phase angle associated with this FRF. So, in multi-degree freedom system, say with 3 degrees of freedom, there are 3 regions where resonances can occur. This is in contrast with single degree freedom system where there can occur 1 resonance. This is a plot of H13, this is the amplitude, this is the phase. This is for H12 of omega. This kind of gives an idea how these functions look like. We can now consider the problem in time domain. Instead of driving harmonically, we can now apply impulsive forces. Suppose I now consider say multi-degree freedom system with the s degree of freedom driven by an unit impulse force. So, the equation would be mx double dot plus cx dot plus kx into f of delta of t, where delta of t is the Dirac delta function, and this f is a vector whose elements are all 0 except the sth element which is unity. So, again we denote x rs of t as the response of rth coordinate due to unit impulse driving at the sth coordinate. So, this analysis is quite similar to the analysis that we just completed in frequency domain, except that now instead of applying harmonic excitation, we are applying an unit impulse. So, we have to conduct a transient analysis. In steady state the system goes to 0. So, what is of interest here is the transient response. So, here again we make the transformation x of t is phi into z of t, where phi is the modal matrix having these orthogonality properties, phi transpose m phi is I, phi transpose k phi is lambda, and C again is taken to be classical with phi transpose C phi being a diagonal matrix as before. Now, I substitute this into this, I get this equation m phi z double dot plus C phi z dot plus k phi z is equal to f delta of t. I pre-multiply now by phi transpose I get these matrices. These are the mass, damping and stiffness matrix in the transform coordinate system. This is the generalized force in the transform coordinate system. This phi transpose m phi is an identity matrix, because that is how we have normalized the modal matrix. This is phi transpose c phi is gamma z naught z dot, and phi transpose k phi is capital lambda. So, these equations are now uncoupled. So, I can take up individual equations and try to solve them. So, if I now consider the nth equation, I get Zn double dot plus 2 eta n omega n Zn dot plus omega n square Zn is summation j equal to 1 to n phi j n f j Dirac delta of t. Now, this f j is 0 except for when j is equal to s, when it is unity. Therefore, this will contribute only when j is equal to s, and I get this expression. So, this is system, we are assuming the system is starting from rest. So, consequently, now Zn of t is obtained as phi Sn by omega dn exponential minus eta n omega n t sin omega dn t, because the response of this system to unit impulse response is Hn of t. So, it is scaled version of that multiplied by this, and we get this. Now, if we return to the physical coordinates x is equal to phi z and look at the rth coordinate, this is summation n equal to 1 to n phi r n Zn of t. For Zn of t, I will now substitute this, I get this expression. So, this is the response of rth coordinate due to an unit impulse applied at sth coordinate. So, it is a generalization of notion of impulse response function for a multi-degree freedom system. This is now expressed in terms of a modal summation. So, all the parameters that appear on the right hand side are essentially obtained in our free vibration analysis. These are the elements of modal matrix. Omega dn is the damped natural frequency of the nth degree of freedom, eta n is the damping in the nth coordinate, omega n is the natural frequency in the nth mode. So, I can now construct the solution at rth degree of freedom. This is what I get. Here again we can notice that this function is symmetric, and if we assemble all elements of this impulse response functions into a square matrix, we call this matrix H of t as matrix of impulse response functions. So, the notion of a impulse response function for a single degree freedom system now gets generalized, and we get, instead of getting a scalar function, we get a matrix, and this function, this matrix is symmetric. Again, as I pointed out already, we need not include all the modes in this modal summation. We can include the first few modes on which we have greater trust. Now, once I find the impulse response function, I can use the Duhamel integral concept, and if I now assume that instead of unit impulse there is a load Fs of tau I applied at the sth degree of freedom instead of unit impulse excitation, then the response remaining, all other things remaining the same, that means all other degrees of freedom are not driven and system starts from rest, I get the response in this form. So, knowing the impulse response function, I can construct the response to an arbitrary load. Okay. So, here again I get a convolution integral, but this is now this gets buried inside. Now, there is a summation here that needs to be factored in while interpreting this integral as a convolution integral. So, we can consider the same example. Instead of applying unit harmonic excitation, now I apply a unit impulse and I solve this problem, and I get x1, x2, x3 that leads to h11, h12 and h13 of t, one column and one row in our impulse response function matrix. So, if I repeat this exercise, by that I mean after completing this, you now apply unit impulse here and measure the response, then you apply unit impulse here and measure the response, you will get a 3 by 3 matrix of impulse response functions, and this constitutes one of the ways of studying dynamical system in a laboratory, and these impulses are applied through instrumented hammers, and measurement of these impulse response function is an important activity in a dynamics laboratory. So, I have numerically solved the equation using this summation. We have already seen what are the eigenvectors and damping and all the numbers we have computed. So, if I plug that in, I get this is the element H11 of t, and as expected, as time tends to infinity, the system comes to rest. But the transients here, you can see that they consist of more than one modes. There are more than one harmonics which are getting superposed here, and actually all the modes are participating in the free vibration decay. Whereas, in a single degree freedom system, you apply an unit impulse, the decay of the oscillations there will contain only one frequency, that is the system natural frequency in that case. But whereas here, the response would consist of contributions from all the three modes. This is plot of H12 of t. Here again there are participation of different modes. For instance, here you can see that, but this decay is dominated by a single mode, as you can see here, and this is for the third degree of freedom system. Initially there is some influence of more than one modes, but eventually the decay is at basically one frequency. We have already seen in the discussion of single degree freedom system that the impulse response function and complex frequency response function form a Fourier transform pair, and that property continues even for discrete multi degree freedom systems. And if you recall the definition of a Fourier transform pair for a function f of t and f of omega, we can show that the impulse response function Hij of t and the complex frequency response function Hij of omega form a Fourier transform pair. So, I leave this as an exercise for you to do this. Now, equipped with this background on deterministic analysis of multi-degree freedom systems in time and frequency domain, we are now ready to consider the problem of random vibration of multi-degree freedom systems. So, we will start by considering MDOF systems under stationary vector random excitation. So, we will consider first the response analysis in the frequency domain. So, we consider the equation of motion mx double dot plus cx dot plus kx equal to f of t, and we assume that the system starts from rest. X of t is a n cross 1 vector, that means this is a n degree freedom system. We assume that the mean of this process, vector random process, is 0 and its covariance is given by RFF of tau. So, this is a n cross n matrix, because this is n cross 1, this is 1 cross n, and we get this as a square matrix. This to superscript t is the transposition operation. So, RFF of tau is actually a n cross n matrix. We are assuming that all degrees of freedom are driven by one component of f of t. So, we are basically interested in characterizing the response of this system in the steady state. So, in the steady state, we can write xt of omega as h of omega into ft of omega, where h of omega is a matrix, xt of omega is the Fourier transform of a truncated time history of x of t, where between 0 to capital T it is equal to x of t and beyond that it is 0, and this we have already discussed when we defined Fourier transforms of aperiodic signals. So, the same idea is being used here, and this is the definition of the matrix of power spectral density functions. Since x of t is now a n cross 1 vector, this power spectral density function will be a n by n matrix, and this is defined as expectation of 1 by t x t of omega x t star transpose omega as t tends to infinity. So, this is conjugation and transposition. So, this is n cross 1, this is 1 cross n. So, the product is n cross n. So, now for x t of omega I will use this, I write h of omega f t of omega, and for x t star t of omega I write this, I get this. Now, in this expression the randomness is involved with f t of omega and its conjugate transpose. So, h of omega and h star of t of omega are deterministic. So, the expectation operator can be taken inside. If I do that, I get the output power spectral density function is now given by h s into h star t. So, this is a generalization of what we got for single degree freedom system as h of omega whole square SFF of omega. This is what we saw for single degree freedom systems. Now, this is for MDOF system. The elements of h of omega, I have already described how to compute them, either directly in terms of MCK or in terms of the natural frequencies and mode shapes. Essentially, if we are looking response in the steady state, the power spectral density function is a complete description. So, this analysis completes the analysis that we intended to do at the outset. That means, we have found out the output power spectral density function, matrix of output power spectral density functions. Now, we can repeat this exercise by considering the response analysis in time domain. Here, of course, there will be a transient state and a steady state. The steady state, of course, would correspond to what we have seen just now, but time domain analysis also includes transients. So, that we will see how it emerges. So, we consider again the same system mx double dot plus cx dot plus kx equal to f of t, and f of t is has 0 mean and a covariance matrix RFF of tau. Now, this vector x of t is now given in terms of matrix of impulse response functions. So, this is n cross 1, this is n cross n, this is n cross 1. F of tau is a random process, vector random process. So, now if I take the expectation on this, I get expected value of x of t is this matrix h of t into expected value of f of tau, and this is given to be 0. Therefore, mean of x of t becomes 0. Now, we can consider the response at t equal to t1. I get x of t1 is 0 to t1 into this. I can also write the response at t equal to t2, I get this expression. If I now take transposition of this, I get xt of t2 as ft of tau 2 into h of t2 minus tau 2 transpose. This is actually symmetric matrix. So, we can omit this t, but although I have retained it. So, now if I multiply this, this is n cross 1. So, this is 1 cross n. So, I can multiply that. So, if I do that, I get a double integral, and if I take the expectation and take the expectation operator inside, I get this expression shown here, and this expected value is nothing but RFF of tau 1 comma tau 2, and since f of tau is given to be stationary, I get this. So, this is n cross n, this is n cross n, this is n cross n, this is n cross n. So, this is the response characterization using matrix notations. So, this again completes the response in analysis in time domain. We can redo this analysis by considering the solution in terms of normal modes. Suppose before I do the random variation analysis, if I were to make the transformation, x of t is phi z of t, and for kth degree of freedom I get this summation, and this Zn of t is governed by this single degree freedom system, and Pn of t is the generalized force, and we have seen that P of t is phi transpose f of t. So, using that I get for the nth element here I get this summation. So, Zn of t now in scalar notations, in scalar form is now given by Hn of t minus tau into this forcing function. Xk of t now therefore is obtained by using this transformation. All the modes need to be summed. If I do this, I get xk of t in terms of a double summation. Now, based on this expression, we can of course evaluate the mean and the covariance and other moments of x of t. Here I have got the response characterization in terms of the natural frequencies and normal modes of the system. As an illustration of these formulations, we will now consider how do multi-degree freedom systems respond to earthquake like support motions. Here I have shown a typical pipeline in a industrial structure, and this orange elements are the supports, and these supports receive differential support motions in the event of an earthquake. So, this piping is housed inside a civil structure. So, in the event of an earthquake, the civil structure oscillates, and these points are of the piping are connected to the slabs and beams and walls of the civil structure, and due to the oscillation of these building components, this pipe also oscillates, and since these connections are at different elevations or different points on the structure, the supports suffer different support motions. So, if you make a finite element model for this, this second view graph shows the how a finite element model is made using line elements, but this aspect is not important for our discussion. This is shown for completeness. A simpler class of problem would be a building frame which is subjected to support displacement u of t, and again if we assume slabs are rigid and heavier compared to columns and columns are flexible, etc., the usual shear building model assumptions, we can approximate this by a 3-degree freedom system where the support motions now appear here as support displacements. So, this u of t now is a scalar random process, its mean is 0, and suppose if it is a stationary random process, its autocovariance is given by r u of tau. So, we can write the equation of motion. Now, u of t is appearing here, this we have seen in the previous lecture. So, if we now introduce the x1, x2, x3 coordinates which define the relative displacement with respect to the ground, the relative displacement of the masses with respect to the ground, I get this as the equation of motion, and the effect of support motion appear as external forcing m1 u double dot, m2 u double dot and m3 u double dot. So, I can cast this equation in the matrix form. This is mx double dot plus cx dot plus kx is equal to minus m, this column of unit elements 1 1 1 into u double dot of t. There is only one time history here, but different multiples of this acceleration m1 into u double dot acts on first floor, m2 into u double dot acts on the second floor, and so on and so forth. Now, we need to analyze this equation when u double dot of t is a random process. So, we can follow the matrix notations to start with. Suppose if I write the equation as mx double dot plus cx dot plus kx equal to f of t, where f of t is minus m unit column vector u double dot of t. Now, if you are interested in analysis in frequency domain, I can consider the Fourier transform of the input f t of omega as this, and if I want the power spectral density of the input effective forces, I get m unity, I have to multiply f t of omega by f t star of omega and take the expectation. So, what I am doing is limit t tending to infinity 1 by t expected value of f t of omega f t star of omega. So, this is contribution, this is f t of omega, f t star of omega will be the will come as u t star transpose of omega, this unit vector transpose, m transpose is unity. So, the expectation operator applies only on the random components. So, I get sxx of sff of omega as this m into unity s u double dot of omega unity transpose m. So, this is the power spectral density function of the excitation. Now, output power spectral density is h sff of omega into h star t of omega. So, I have now this expression, I plug it in here and this is the PSD that I am looking for. So, if you are doing a coding on computer, this is very easy to implement. H of omega here is the inverse of the dynamic stiffness matrix, and we have already seen that this can be computed in terms of the normal modes of the natural frequency and normal modes of the system. Now, you want to do a time domain analysis, again the analysis is straightforward. F of t is now this mean is 0 because mean of u of t is 0. If you want now the matrix of autocovariance function of f of t, I have to find expectation of f of t1 into f transpose of t2. This is a n by n matrix. So, for f of t I have got this expression. Now, if I substitute here, I get this expression. This is f of t into f t of t2. So, this is what I am getting, and expectation of runs only on u double dot of t. So, this is RFF of t1 comma t2. So, this is nothing but m unity r u double dot of t2 comma t1 into unity transpose into m. Now, I know x of t is given by this. This is a matrix of impulse response function. This is the applied excitation. Now, f of tau itself is given in terms of m into unity u double dot of tau d tau. There is minus sign here, and expected value of x of t is 0. And if you want now the autocovariance of x of t, you have to take expected value of x of t into x of t2 transpose, and if you do that, you get this expression. These are all in now matrix notation, and we can evaluate this to derive the covariance. In terms of the generalized coordinates, I can make the transformation x is equal to phi y. I am using y because z I have used for total displacement. So, for xk of t is given by this now. So, we can find out the expression for the effective force for the nth coordinate nth degree of freedom by using this relation, and this quantity phi transpose m into unity, this one is given a name, it is known as modal participation factor. So, I get the equation for nth generalized coordinate as yn double dot plus 2 eta n omega n yn dot plus omega n square yn into gamma n u double dot of t. For different values of this n, the right hand side is simply scaled by this participation factor. The time history remains the same, but it gets factored by multiplied by gamma 1, gamma 2 or whatever the nth mode, it is gamma n. This gamma itself is function of the modal matrix and the mass matrix of the system. So, x of t is this, the transformation, this is the modal matrix, and xk of t is this. So, if I now write yn of t in terms of impulse response of nth degree of freedom system, I get this expression. So, substituting this into expression for xk of t, I get xk of t to be given by this. Now, I can launch the calculation of response moments. So, you want now the mean, you take the expectation of this, expected value of u double dot of t is given to be 0, therefore, expected value of xk of t is 0. And if you multiply now xk of t1 into xk of t2, you get the, you need to compute the expected value of yn of t1 and ym of t2, and if we do that, I get this double summation. And this expected value of u double dot of tau 1, u double dot of tau 2 is this, because u of t is given to be stationary. So, this is actually the autocovariance of response that I am looking for. In this, if I take t1 equal to t2, I get the variance which is given by this expression. So, if you know now the autocovariance, you have to, now the task is reduced to evaluation of these integrals. This analysis can also be done in frequency domain. To see that, we again begin with the transformation xk of t, x of t, and xk of t is given by this. Now, I take the Fourier transform of this, I get this expression in terms of the Fourier transform of the generalized coordinates, the truncated Fourier transform of the truncated time histories, and the expression for y and t of omega itself can be derived by using the governing equation, and one gets in terms of participation factor and Fourier transform of the u double dot of t, and this is the expression that we get. So, if I now substitute the expression for the generalized coordinate into the expression for the physical coordinate, I get this expression. Based on this, now I can compute the power spectral density of xk of t, that is actually limit t tending to infinity of 1 by t of expected value of x k t of omega x k t of omega conjugate. So, I have found out this expression, I can find this conjugation and multiply. If I do this, this one single summation becomes double summation and I get this as the output power spectral density function. This is the quantity that we are looking for. In this expression we can do the following. We can sum up all the diagonal terms, that means I will take the summation when n equal to m. So, I get n equal to n, I get this term where I have n equal to m, therefore, all these quantities now become real and this is the expression. These are the off diagonal terms, contribution from off diagonal terms. So, I can now find the variance of the process x k of t by finding area under this power spectral density function. Area under this first term can be viewed as contributions that ignore the modal interaction. This second term where n not equal to m is contribution due to covariance or cross covariance between different normal modes, the different generalized coordinates. Therefore, this can be viewed as some kind of correction due to modal interactions. Now, this description becomes important later when we discuss relationship between response spectrum based analysis and power spectral density function based analysis for earthquake response of structures. There a question on rules of combining modal contribution arises, and those rules are essentially formulated by investigating these expressions, and we will return to this later when we will discuss the modal combination rules in response spectrum based analysis. This kind of division into one that ignores modal contribution and one that corrects it can also be done in time domain. Here again in this summation also I can first sum the terms where n equal to m and get the second set of terms which represents cross correlations between different modes. So, if all our calculations are right, as t tends to infinity, whatever we get here in time domain analysis should match with this analysis. This is valid only for steady state. So, such a match we have already seen for single degree freedom system under random excitations. So, to illustrate this idea, I have considered a building frame under random support motion, and this support acceleration is modeled as a Kanai-Tajimi power spectral density function. So, this itself if you recall was obtained by passing a white noise through a soil layer, and the absolute acceleration at the top of the soil layer was taken as the input to this building. Now, if we do the random aberration analysis in this case, this is actually the input power spectral density that is actually used in the numerical work. The Kanai-Tajimi power spectral density function, as I mentioned, applies a white noise at the bedrock level. This is bedrock, this is soil, and we are interested in how this top of the soil layer oscillate, and we have modeled this soil layer as a single degree freedom system, and consequently when you look at the power spectral density of the absolute acceleration at the top of the soil layer, it will have one resonant peak. This peak corresponds to I think I have taken it as 4 pi radian per second, and this bandwidth corresponds to a damping in the soil layer, and this is kept at a fairly high value 0.53. So, this is the power spectral density function for that we are assuming for the ground acceleration. If you carry out the response analysis using the methods that just now outlined, I get the power spectral density functions, the auto power spectral density functions for the 3 degrees of freedom x1, x2, x3. So, the black one is for x1, the red one for x2 and green one for x3. So, this is the displacement auto power spectral density function for the 3 coordinates, and the power spectral density function itself is expressed in these units. So, you can see here the power spectral density function, as you could expect, is dominated by first mode, because the first natural frequency is around 14 radian per second and the soil frequency is around 4 pi, which is again close to some 13 radian per second. So, the first mode dominates the behavior and the second and third modes make marginal contributions to the total response. Mind you that this y axis is on log scale. We can also look at the cross power spectral density function between response at different floor levels. That cross power spectral density function would be a complex valued quantity. Therefore, we can talk of an amplitude function and a phase function. So, this what is shown here is the amplitude of cross power spectral density function between x1 of t and x2 of t. The phase spectrum is shown here. So, this completes the analysis of structures such as this, where all the supports of the structure essentially receive identical support motion. A generalization of this problem would be when different supports receive different support motions. So, we will briefly indicate what exactly is the problem there and consider the detailed discussion in the next lecture. So, here what we are considering is a structure something like this. Suppose we have made a computational model, say using finite element method. This A, B, C are supports. Suppose we assume that these supports are subjected to displacements. There are 6 displacement components which are different from each other. So, this I will call it as UG1 of t, UG2 of t, UG3 of t, and so on and so forth. This is a frame structure made up of beam elements. So, the degrees of freedom that a node here will have are 2 translations and 1 rotation. So, if you look at this entire structural model, there are now degrees of freedom associated with the ground, these points I call it as ground, and degrees of freedom associated with the superstructure. So, the total degrees of freedom can be classified as some ut of t and ug of t. This superscript capital T indicates total response and ug of t are the applied support displacements. So, if you write now the equilibrium equation for the entire structure, I get the equation in the standard form mu double dot plus cu dot plus ku equal to some f. But I have now partitioned the displacement degrees of freedom into ut and ug of t. These are unknown degrees of freedom of the superstructure, and ug of t are the applied support displacements. This ug of this ut, there are, let us assume that there are capital N number of unknowns, whereas this ug there are ng number of degrees of freedom. This Pg of t here on the right hand side, Pg of t are the reactions. There is no external forces other than the support motion, therefore, this element is 0. So, based on this partitioning of the displacement vector, I can also partition now the mass, the damping and stiffness matrices, and we can consider these equations separately. This m, c and k that appear here are n cross n, and this mg, cg, kg are n cross ng, and these mgg, cgg, kgg are ng cross ng matrices. Now, before we look into the detailed analysis, we can consider certain response features without actually looking into the solution of the equilibrium equations. Imagine that these support displacements are applied statically. Then there will be stresses in the structure because of differential support displacements, even purely under static conditions. Now, if these support displacements are now dynamic, there will be a pseudo dynamic response which is purely caused purely due to differential support displacements and which is not affected by the inertia of the structure. So, the total response can be decomposed into two vectors, a pseudo dynamic component and a dynamic component. In analysis of structures of this kind, it is important to delineate the contributions to the response from the pseudo dynamic component and dynamic component. So, when we analyze this problem, therefore, we need to formulate the problem in such a way that we will be able to output the properties of pseudo dynamic component of the response and the dynamic component of the response. So, this problem we will formulate in the next lecture and we will conclude this lecture at this stage.